Topics in Post-Harvest Technology. Refrigeration Systems, Part 2. In Part 2, we will discuss refrigerants with special emphasis on ammonia, evaporators, and the benefits of minimizing temperature fluctuations in storage. First, let's talk about refrigerants. Many refrigerants are available. Commercially, from moderate to large systems, ammonia has been a preferred refrigerant. Ammonia is relatively inexpensive and does not require high pressures to facilitate a change from a gas to a liquid. Ammonia also has a relatively high heat of vaporization of 590 BTUs per pound at 1 atmosphere. However, ammonia is potentially lethal, and if there is a leak, it can destroy not only stored produce, but can also kill employees. Ammonia is also explosive at concentrations of 15 to 28% in air. As a result of these concerns, a refrigeration engineer must be present or on call 24/7 to handle any problems. Refrigerants have been developed which are not toxic or explosive and which are used in moderate to small systems, such as home refrigerators. However, though safer than ammonia, these refrigerants are much more expensive and historically were strong ozone depleters. An example of a previously widely used ozone-depleting refrigerant is R22. The R simply means refrigerant. Since the 1970s, there has been a strong push to develop refrigerants that have low impacts on the Earth's ozone layer. Ammonia does not deplete the Earth's ozone layer. Let's talk about evaporators. There should be only a 2 to 3 Fahrenheit temperature difference between the net temperature of the evaporator coils and the air in the storage room. This minimizes frost buildup on the coils and limits the potential to lose water from stored produce. If the evaporator coils are too cold, as the storage room air goes over the coils, the water in the air will immediately freeze to the coils, reducing the relative humidity of the storage air. As this drier air moves over the stored produce in a room, water will move from the produce into the air, leading to wilting and decreased shelf life. So by having only a 2 to 3 degree difference in temperature between the storage air and the evaporator coils, water loss from the produce as well as ice buildup on the evaporator coils will be minimized. Maintain efficiency, and regardless of the temperature split, the evaporator coils will need to be periodically defrosted to remove the ice which accumulates. This can be done by using electricity to heat the evaporator coils, using warm air or water flowing over the coils, or by flushing the evaporator coils with warm liquid refrigerant or hot refrigerant gas. What about temperature fluctuations in the storage environment? Refrigerators cycle, that is, they periodically turn on and off, so there are recurring upper and lower temperatures within a cooler. The better the cooler design, the smaller will be this fluctuation or range in temperature. This is a thermograph showing temperature changes in a cooler over time. You'll notice the temperatures were recorded from December the 13th to about January the 10th, so nearly a month. The thick black line at the bottom of the graph actually indicates the overall high and low temperatures in the cooler. The taller lines represent the periodic but temporary defrost temperatures in the cooler. So when you set up the refrigerator for a cooler, you try to limit how long and how often you're going to defrost the evaporator coils to minimize temperature increases in the cooler. If defrosting too long, the higher temperatures will have deleterious effects on your produce, as even temporarily, the respiration rate can go higher, water loss can increase, and decay can increase. You will want to defrost just long enough and just often enough to prevent frost buildup on the evaporator coils. In the cooler that was monitored, the average temperature was 3.5 degrees Celsius, or about 38 degrees Fahrenheit. There was a significant standard deviation in temperature of about 2 degrees Celsius, or 3.5 degrees Fahrenheit. The maximum temperature due to defrosting was 12.8 degrees Celsius, about 51 degrees Fahrenheit. The minimum temperature in the cooler went down to 0.3 degrees Celsius, which is 32.5 degrees Fahrenheit. We really want to be careful that we don't go below freezing, because we could potentially get localized freezing of product in the storage room. Minimizing temperature fluctuations in storage may have to be balanced with cost considerations. Having a tighter and more precise refrigeration system can mean a bigger refrigeration unit, more refrigerant, and or running the system more often, all of which will be more costly. However, for some crops, such as apples that we store long-term for up to 12 months, variations of 2 to 3 degrees Fahrenheit are too great for their long-term storage. We need very tight or precise storage so that we can get them to last for those full 12 months. With large temperature swings, we can get freezing damage or moisture condensation on produce, leading to staining and increased rot. If the temperature increases and the produce loses more moisture, when the temperature goes down, the air can reach the dew point. That's the point where the relative humidity has increased to 100% and water starts condensing from the air. This water will settle on the surface of the product, which can lead to surface staining, which affects marketability, and increased microbial growth and rot. Temperature variations are minimized by having a well-insulated storage room, having adequate refrigeration capacity, and by stacking the cartons and placing the pallets properly to promote uniform airflow within the storage room and around the product. So what are the takeaways? A common refrigerant used for moderately large to large refrigeration systems is ammonia, but it is toxic and potentially explosive. For smaller refrigeration systems, refrigerants have been developed that are not hazardous or explosive, but historically they have been ozone depleters. The current trend is to build refrigeration systems that utilize non-ozone depleting refrigerants. There should be only a 2 to 3 degree Fahrenheit difference between the coils of an evaporator and the air being cooled. The frequency and duration of evaporator defrosting should be minimized to prevent excessive warming of cold rooms. The smaller the difference between the high and low temperature within a room, the longer produce can be stored.